All right, so in this worked example, we're looking at the learning objective that students will be able to relate base units to derived units, or relate derived units to the base units in the metric system, the SI system. And the question number 1 from ACE Physics paper 9702, paper 22, May, June 2014, for anybody that wanted to queue that one up and follow along, says show that the SI base units of power are kilogram meters squared per second cubed. Now, we haven't really gone over work, energy, and power, so I'll have to tell you how we define power. Power is equal to the work divided by the time. Work over time. Good life advice and the definition of power. The rate of change of work, the rate of change at which one form of energy is converted to another is another way to think about it, because work and energy are really kind of the same thing. We define energy as the ability to do work. So one way to think about power is the rate at which one form of energy converts into another one, like the rate at which our sun converts the nuclear energy into heat energy or light energy, or also the rate at which work is done. Now, work is defined as force times displacement. So you apply a force over a displacement S, and that's the work done. And that's still T for time. So power is really force times displacement divided by time. Those are the quantities that sort of go into calculating power. So on this top line, I could list, these are quantities. And down here, I'll put my units. Now, you just have to have some strategy for how are you going to show sort of the corresponding units that measure those quantities, okay? So the derived unit of power, watt, is the unit of power. The unit of work, or energy, is the joule, and the unit of time is the second. So here we've got a perfectly valid way to represent how the units of these quantities are related. A watt is a joule per second. Right? So the rate at which energy is converted, the rate at which energy is done, the rate at which work is done. So joules per second, same thing as watts of power. Watt is the unit of power. The problem with this is that we haven't done what the question asked, which is show that the SI base units of power are kilogram meters squared per second cubed, right? So we need to sort of boil this down all the way to the base units. So a joule is the same thing as a Newton of force times a meter of displacement, and there's still a second of time. Now here we should really be careful about the alphabet soup of physics. So this S up here clearly represents displacement, and this S down here clearly represents seconds of time, right? That S is different than that S. You have to just really look at the context in which you see those variables. If there's any confusion about that, then you can, write out seconds, write out displacement for that. So remember, S is the letter we use to represent the quantity displacement. All of these are quantities here on this line. We use the lowercase letter s also for seconds, seconds of time. So you don't want to confuse those things, right? All of these here are units, all of these here are quantities. Now we still haven't gotten to this, kilogram meters squared per second cubed. That's what the base units of this watt should be. So far, we've got it to a Newton meter per second. Which of these is not a base unit? Newtons, meters, or seconds? Which one of those three units is a derived unit? Yeah, the Newton, right? On the chalkboard over here, it kind of says that. So what is a Newton equal to? Does anybody know that? Referencing the same chalkboard. Kilogram times meters per second squared. So really we're just sort of saying, well, and if you want to, you can put another equation up here. You can say, well, now I need an equation for force, F equals ma, right? One we've already kind of worked with. And that will remind you what's on the chalkboard over there, that a Newton, which is over here, is really a kilogram of mass times a meter per second squared of acceleration. So I'm going to substitute those units in for newtons here. And we're going to get a Newton is a kilogram meter per second squared. I prefer to have positive exponents. And so like rather than writing with a negative index like you kind of see on the chalkboard, like s to the -2, I'd rather just put that in the denominator with a positive 2. So it's like kilogram meters per second squared. Those are just the units of this Newton. Those are the base units of the derived unit of Newton. What else do I still need over here? Still have to have that meter, still have to have that second in the denominator. So that means in the numerator, I'm gonna have meters times meters, and I'm gonna have these seconds squared that came from the acceleration times the second here that came from this time. Once you've kind of got it like this, you wanna put it all back together again to make it resemble that. Like a meter times a meter is a meter squared, and seconds squared times seconds is seconds cubed in the denominator. Now we can rewrite it a little bit more cleanly with a negative index. So this is the kind of working that shows the base units of power. The watt is the derived unit, are kilogram meter squared per second cubed. A watt is a kilogram meter squared per second cubed, just like a Newton is a kilogram meter per second squared. So 1 Newton of force, remember, was all this right here. There's our Newton. So a Newton meter per second, right? Newton meter per second. It's all sort of the same here. You're just sort of expanding the derived units until they're all base units. And that'd be worth 3 marks there. And really, if you practice this a lot between now and the time you're sitting for like an ACE physics paper, these sorts of marks will be readily available. It seems confusing to students when they first learn it, but it really is such a helpful tool to have at your disposal when you're doing calculations to check the units out. You know, oh, well, we should expect these units. Do we get these units if we actually, you know, divide everything with the units there? And if you don't, you'll find a mistake. You know, like I said, the units sort of have to work out. Let's keep a good thing going here and do part B. It says, the rate of flow of thermal energy, Q over T, in a material is given by Q over T equals C times A times T over X, where A is the cross-sectional area of the material, T is the temperature difference across the thickness of the material, X is the thickness of the material, and C is a constant. And our job is to determine the SI base units of C. Now that might seem impossible to you right now. So like, I have no idea where to begin. We just learned this thing right now. Does anybody feel like, you know, if you gave me a minute though to think through it, I might be able to come up with something resembling a correct answer. And if so, go ahead and take a head start right now. Try to just go with it, okay? I'm gonna give a little bit more explanation, some hints, and I want students that it's always good, like you're given a new puzzle, try to think, you know, through it yourself first before you say, well, I'll just wait for the answer. You know, sort of wrestling through it in your mind is one of the best ways to learn. So the strategy here to get the units of C, the base units of C, are going to be, we have to know everything else, first of all. We got to know everything else in this equation, and then C is just going to be whatever it must be in order to make them equal. Okay, like we have to have the same units on both sides. So whatever the units are for Q over T, the units of CAT over X have to be that. And so C is just some constant. And sometimes in an equation, we need a constant to like correct for something. For example, like astronomy I mentioned earlier. There's an equation that sort of governs how much energy a planet will put out, will sort of expel based on how much radiant energy is incident upon it. But the equation is very simple in the sense that it doesn't account for like the reflective surfaces, you know, so like if we had an ice world that reflected a lot of the sunlight, we would need to correct for that. We need some constant in front of the typical equation that we would use to calculate, you know, like power in, power out for a planet coming to thermal equilibrium that's a certain distance away from a star. This is how we calculate like the Goldilocks zone, or we say, oh, this is an exoplanet that's habitable because it's close enough to its star that liquid water could exist. We have to have sort of equations to be able to do those calculations to say whether or not, you know, exoplanets are habitable. So you really do have to know something about Q here. You have to know something about T. That should be pretty straightforward. I think they sort of define everything else here, but all they tell you is that it's the rate of flow of thermal energy. Well, that's kind of a nice clue there. So we're going to start with these equations, and we're going to substitute in the units just like we did here. We're going to figure out the left side, figure out everything on the right side besides C, and then that'll be like the last piece of the puzzle. Whatever C has to be to make it equal. All right. Does anybody know the units of Q? I'm going to rewrite the equation just for completion's sake here. So we have Q over T equals cat over X. And again, I want to be very precise to say these are the quantities that are related, right? Equations relate quantities. Now, what units do we measure these quantities in? Does anybody know the unit of thermal energy? Save that for when we get here to temperature. So energy, just like we had up here, work and energy are the same thing, measured in joules. Okay, joules of energy. Doesn't matter if it's heat energy, electrical energy, energy measured in joules. So I'll just write out the whole word, and then from now on, I'll just call it J. So that's a unit for energy. How about the unit of this quantity? What's the unit of that quantity? What is that quantity? That's not temperature. Remember, capital T on this side is temperature. That's another thing. Take care, right? All they tell us about Q over lowercase t is right here, the rate of flow of thermal energy, Q over T. So it's going to be seconds, right? Because it's a rate. So it's energy per time. Hey, doesn't that sound familiar? Work per time, energy per time. In other words, one calculation leads to the next. This is a power. Okay. In other words, we've already solved it over here. We solved the left side. The left side should be this because it's a power, right? It's energy per time. So if we have joules per second, excuse me, if we have joules per second on the left side, and we already know that a joule per second is a Newton meter per second is a kilogram meter squared per second cubed, you see how those are the base units of the left side of this. Like they had us do this working up here because it helped us out here. You just have to connect that, oh, that's a power too. Q over T is a power. It's a rate of energy. So I'm just going to kind of write that over here on the left side. We know that we've got kilogram meter squared per second cubed. And again, I like positive exponents. And so I know that a kilogram meter squared per second cubed is a watt, right? A joule per second is the same thing as this. So we've kind of proved up here. Joule per second is that. They told us. Now let's think about the right side of this equation, the units that we measure the same thing. Now, does anybody know the units of C? If you did, you'd be done. That's what we're solving for. Like no one knows it yet. Okay, so we're just going to leave that as like a C. I kind of like to remind myself that that's what I'm solving for, like open brackets with kind of like a question mark. Or you just leave it as C. So it's like that's the thing I want to know. Like I gotta put whatever in this question mark box that must go there in order to give me homogeneity, sameness. It's gotta be the same on both sides. How about A? Cross-sectional area of the material. Does anybody know what units we would measure cross-sectional area in? Meters squared, right? Because it's an area, length times width. So meters squared, right? That's A. The units of A are meters squared. How about T is a temperature difference? Degrees Kelvin. How about X down here in the denominator? What are the units of X? Say it again. It's not mass. X is the thickness of the material. I heard somebody say it's going to be meters, right? Thickness, like how would you measure the thickness of something? It's a distance, right? It's a distance, so meters. The base unit, all we care about is the base unit. You might say, well, the thickness of a material, we would use centimeters or millimeters. Yeah, but the base unit is meters, right? It's a length. So on the left side, we've got kilogram meters squared per second cubed. And so far on the right side, let's clean this up a little bit. This meter is going to cancel one of those. And so what we have so far is our question mark here. We're going to have to fill in some things. And we've got meters and we've got Kelvin. Okay. Now let's think about what must go in this question mark box in order so that meters times Kelvin equals kilogram meters squared per second cubed. We know we're going to have another meter in there. Okay, so question mark, we know we need a meter. So then we multiply it by this meter, we'll get meters squared. What else has to be in that question mark box? We need per seconds cubed, right? It has to be in the denominator. So question mark has meters per seconds cubed. Yep. Anything else? We need a kilogram, right? There's no kilograms in this yet. But there has to be, because on the left side there's kilograms. And so the units of C must be kilogram meters per second cubed. Are we missing anything else? If we were to plug this in to here, we would have kilogram meters squared Kelvin per second cubed, and that does not equal kilogram meters squared per second cubed. We need a what? We need a per degree Kelvin, right? A Kelvin in the denominator down here will cancel out the Kelvin on this side. In other words, if we plug in this for question mark for C, then that should give us the correct answer. Let's just substitute and make sure. So we knew we were going for kilogram meters squared per second cubed. And on the right side, we've deduced that the question mark should be kilogram meter per second cube per Kelvin. And then we still had this, meter times Kelvin out here. So does this work out? The Kelvins are going to cancel on the right side. The meters and the meters here are going to be meters squared. And indeed, we've determined that the SI base units of C must be that. So we'll write our final answer more cleanly. Kilogram meter per second cube per degree Kelvin, like that. And that's your final answer worth 4 marks.